So now on to our official recap of buffers. I'm going to do it a bit differently and do the recap in the form of a clicker. Now, because it's part of the actual recap, I will answer the clicker question in this video, but quickly pause it and just go through this yourself and see what you come up with. So you should have gotten answer C, and I will still officially make this available in Zoom, but let's just go through that. A buffer is 1. A solution that regulates pH. Correct. 2. A solution containing significant amounts of a strong acid and its conjugate base. Incorrect. A buffer is in fact a solution containing significant amounts of a weak acid and its conjugate base, which is Roman numeral number 4. And then we skipped over number 3, a solution whose pH can be described by the Henderson-Hasselbalch equation. That is completely true. In fact, that's the only time you can use that equation to calculate pH, is if it's a buffer. So let's look a bit more into this. Last lecture, we used this buffer solution here as our example buffer, where we had 0.40 liters of a mixture of both formic acid and its conjugate formate ion base. We also saw what happens upon neutralization with 0.10 liters of this strong base here. We had to deal with that reaction in moles because it is 2 different volumes added together, as we covered previously. And then we got this resulting solution here, which was still a buffer because we had significant amounts of both the acid and its conjugate. And that means we could still calculate this new buffer solution's pH using the Henderson-Hasselbalch equation, which looks like this. Chemically speaking, we should use concentrations for these species, but mathematically we can do a shortcut and just use moles. And when we did this problem, we found that the new pH value of this solution had not changed that significantly from the old pH value. So the last concept that we need to learn about buffers is what makes an effective buffer. Because while they can regulate pHs, they can't just regulate any pH range that we want. There are certain rules that we need to consider. So let's learn those. So let's start by defining something called the buffer range. Buffer range. This is the pH range that a buffer effectively regulates. pH range that buffer effectively regulates. And that pH range is equal to whatever the acid component of the buffer's pKa value is, plus or minus 1. And this right here is based on the fact that the concentration of base and acid must be within 10 times of each other. Based on fact that the concentration of base and acid are within 10 times each other. And this is something that you will prove for yourself in the homework. And we will make one important note about these concentrations, that when they are equal, the pH equals pKa. When equal, pH equals pKa. And we get that from the Henderson-Hasselbalch equation, and we saw this when we first learned that equation. But we make the note again because at this point we have maximum resistance. Maximum resistance to pH change. That is the ideal buffer concentration ratio, is equal. And at that point, our pH will actually equal the pKa of the acid. But so long as we're within plus or minus 1 of that pKa value, you've got an effective buffer. So for example, a buffer based on formic acid. Buffer based on formic acid, whose pKa value is equal to 3.74, can moderate pH changes over a range of 2.74 to 4.74. Can moderate pH changes over a range of 2.74 to 4.74. But if you had some solution that you wanted to keep at some stable pH around 6 to 6.1, you would not make a buffer using formic acid and its conjugate base, because that is outside of the range where it can effectively control the pH value. And so there's a clicker to go with this idea, but we will do it in Zoom.